To create accurate maps, cartographers need to have a spatial understanding of the physical environment and area relationships, as well as the ability to abstract and symbolize them. In this video, I'm going to review data types that we have learned about in the past as a refresher so you can better understand why data is symbolized and classified the way that it is. First, I will review the different data characteristics, including whether data is qualitative or quantitative, the different variable levels, and the different data types in tables and databases. Then I will talk about data symbology and classification in map design. Statistical data can be broken into two categories, qualitative and quantitative. Qualitative data is data that is classified as a name or object type, like a state or city name, or things like land cover. In the slide example, the qualitative data is the tree type, including palm trees, pine trees, and oak trees. Quantitative data, on the other hand, is numeric. It can only be represented by a number. In the slide example, the quantitative data is the number of oak trees. Looking back at the qualitative data example, the quantitative data would be the count of the different types of trees. There are 2 palm trees, 2 pine trees, and 2 oak trees, so the qualitative data value of each one is 2. Here is a map created by the CDC in one of their GIS manuals. On the top row, you can see that the data is qualitative by indicating where each hospital, urgent care, and ambulatory surgical facilities are located. On the bottom row, there is a graduated point symbol map showing the total number of facilities in each county. There are also 4 different data levels. Nominal or categorical data is the lowest level because you can run the least amount of analyses on it. It contains data about different categories such as tree or bird species and does not have an order or direction. Ordinal data is ranked data, but the measurements between the values doesn't matter. This includes things like low, middle, and high income levels or Likert scale data. Likert scales are generally questions that ask you to rank something. I'm sure you've all seen them on numerous surveys, and they ask you to decide how much you agree or disagree with a statement with options like disagree, somewhat disagree, neutral, somewhat agree, and agree. Interval data is data where the differences in measurements do matter, but there is no true zero value. This includes things like temperature measured in degrees Fahrenheit or Celsius. 0 degrees Celsius is not the same as 0 degrees Fahrenheit, so the temperature on those scales does not have a true zero. This is contrary to ratio data, where the differences in measurement do matter, but it does have a true zero, like degrees Kelvin. 0 degrees Kelvin is when all particles stop moving and the complete absence of energy or heat. That complete absence is a true zero. The data level determines the type of analyses you can run. The higher the data level, the more tests you can run. In the first 2 rows, you can see that nominal data is the only data type that is not sequenced or ordered. And ratio level data is the only data that has an absolute zero. As for the test you can run, the farther down you go or the more complicated the analysis get, you need a higher level of data or more complicated level of data in order to complete those analyses accurately. Qualitative data includes nominal and categorical data because it does not have a numeric value, and ordinal data because the numbers that are assigned as values do not represent the actual count or true value of the data. The values are assigned. The values are assigned in both nominal and categorical data and ordinal level data. However, ordinal level data is often analyzed as if it were interval level data because more analysis can be run on that sort of data. This is possible because the values are ranked or ordered. So the analyst makes the assumption that the differences between the measurements do matter, like in interval and ratio data. Going back to the Likert scale as an example, you have 5 possible answers ranging from disagree to agree. Each of those answers is given a number value, typically in intervals of 1. There are a ton of different ways you can assign the values to ordinal level data, so as long as the intervals can be justified, you can use them. On the slide, I have two examples of how a Likert scale question can be coded. The first ranges from 1 to 5, and the second from -2 to +2. They're both representing the same answers. If you decide to analyze your ordinal data as interval data, it's essential to understand how it was coded. If you were trying to determine the average level of agreement to a question by calculating the mean, a value of 1 means something completely different based on the two scales. So make sure you know how your data was coded. On to data field types. Text or string data is data that is not a number value, like names, abbreviations, alphanumeric codes, and numeric codes that don't represent an actual value, like zip codes. If the column is classified as a text or string field, you will not be able to run any calculations on it until you convert that column into a numeric data type. Short and long integers can be positive and negative whole numbers. Short integers contain fewer data values than long integers. Short integers are often used in coding, like land use, vegetation type, or Boolean, which is true or false data, often with false being represented as 0 and true being represented as 1. Long integers are usually used for quantity measurements like population, where you can't have a partial value, because long and short integers are whole numbers. Float and double data types are numeric like long and short integers, but they can contain a much wider range of values as well as decimal points. Float data are smaller than double data, and float data are often used for percentages. Double data types can contain many more characters and decimal points, and therefore are used for data that needs a higher amount of accuracy, like latitude and longitude. There are 5 primary ways to symbolize data pertaining to the color and symbol. Single symbol maps are the simplest, as they use one common symbol or color to identify a feature. Unique symbol maps use different symbols or colors for each category. Graduated symbols base the color or symbol size on the data value relative to the rest of the data, and then classifies them into different groups. The larger the symbol or darker the color, the higher the value. Proportional symbols base the symbol size on the data value, just as graduated symbols do, but it's on a continuous scale, which is unlike graduated symbols, so they are not broken into different classes. For example, a single symbol map may have the locations of all the hospitals in a region, like the 3 different qualitative data maps in the CDC example. In this example, the largest map uses unique symbols and colors for each category, with different symbols for the urgent care and ambulatory surgical facilities, while the 3 smaller maps have a single symbol but multiple colors. The 3 maps on the bottom row use graduated symbols, meaning the symbol size increases depending on the data value, and it's broken up into 3 classes, 1, 5, and 10 facilities per county. The same concept can be used for color. In graduated color maps, the color ranges from light to dark, with the highest values having the darkest colors. Proportional symbols are very similar to graduated symbols, except that they aren't broken into classes. Divergent symbols are based on differences in quantitative data. It's similar to the graduated and proportional concepts, but instead of having a range from high to low, it has a center point and the symbols move in opposite directions. You can think about this like a number line, with 0 being the center point and in a pale yellow color, with the positive values changing from pale yellow to blue and the negative values ranging from pale yellow to red. If you run a cluster analysis in ArcGIS, that will be the default color scheme. and showing the areas that have relatively low and relatively high values. Skipping ahead slightly, the bottom map shows a divergent color scheme for the standard deviation of the data. It's the same as I just described for the cluster analysis. Lastly, you can symbolize point data with dot density maps. Just make sure that it's legible. On the right, I have a list of each way you can display the data by each symbol method. In ArcGIS, there are 5 main ways to classify your data to be displayed in your maps. Each has its own pros and cons, so you will need to pick the classification type based on what spatial relationship you want to show. In addition to the 5 listed categories, the way your data will be classified also depends on the number of groups, also known as classes or buckets. All of the data in these examples are from the CDC, and they use 5 classes, but imagine how different the data would look if they were broken into 3 or 10 classes. First, we have equal intervals, with each group having the same range, which is calculated by taking the range of the total variable and then dividing it into the number of classes you want, which makes it very easy to interpret. However, this may not show all the variability in the data because the breaking points are not based on the data distribution. Quantiles separate the data into classes based on the number of observations that each group has. So each group has the same number of data points. Quartiles are separated into 4 classes, with each group having 25% of the data points. Quintiles break the data into 5 groups, with each group containing 20% of the data points, and so on and so forth. However, keep in mind that because this method also breaks classes up by the number of points, it may make the data appear to have more variation as the breaking points were not picked with regards to the data values, and it works best with normally distributed data. Like with quantiles, displaying data by its standard deviation is best done when the data is normally distributed. The mean is calculated and used as a center point, and the standard deviations are then calculated and used to create the groupings, including groups with 1, between 1 and 2, and more than 2 standard deviations away from the mean. This is best when you want to see the outliers in the data. Natural breaks, or janks, separate classes based on where there are gaps in the data distribution. The advantage to this method is that the data distribution is explicitly considered. However, it may be harder for people to understand the different class groups when they are interpreting the map. The number of classes should range from should have no more than 6 or 7. Lastly, manual breaks are just what it sounds like. You determine which values belong to each group. This is particularly useful when you are creating multiple maps to be analyzed together, also known as a map series, or if there are important theoretical values or value ranges that you want to convey with your map.